electromotive force, which is called as EMF, denoted by E. And the second thing we are going to see is terminal potential difference, okay, given by V. Now, to understand electromotive force, we are first going to see its definition. So this is a cell, and the cell has two terminals, positive and negative, and then the cell is connected to a circuit. So this is a circuit. Okay. So over here, what are we going to talk about is, imagine there is a charge. So this charge has to be taken from a lower terminal to the higher terminal of the cell. And then the charge is taken across whole circuit. So the work that is done to take the charge from the lower terminal to the higher terminal of the cell is called as W1. And then the work done to take this charge in the external circuit, that work done is called as W2. So this total work done that is over here, W1 upon W2. And suppose if the charge is Q, then this is called as EMF. So the electromotive force is defined as the energy spent or the work done per unit charge is in taking a positive test charge around the complete circuit of the cell. Okay, so that means from the lower terminal to the higher terminal of the cell and across the cell. So that is called as electromotive force. And this can be termed as small v and big V. So small v is the potential difference inside the cell. Okay, so big V is the potential difference in the external circuit, which is also called as terminal potential difference. Which is also called as terminal potential difference. So now, when I write E as equal to V plus big V, according to Ohm's law, I can write this is I into small r over here. And I'm going to write it as I into big R. So if this is R1, R2, for me, the big R, that is resistance in the external circuit, is R1 plus R2. What is the small r? Small r is the resistance offered by the cell. So let me write down over here, small r is called as internal resistance of the cell. And big R is called as external resistance. External resistance or the resistance offered in the circuit. So I can take I out and I will have small r plus big R. So this is an important formula which will be used in numericals. So there is one more definition given of EMF. So this is a cell. Now you can see that it is just a cell. That means the cell is not in circuit. Or we say that it is in open circuit. There is no current drawn from it. Now, if you connect it to a voltmeter right now, like say this is a voltmeter, then whatever the voltmeter reads is the EMF. So when the cell is not in circuit, it will read the EMF, 1.5 volt, for example. Now, when the cell, you consider the cell to be in circuit. Okay, you connect a circuit, and then current is flowing in the cell. And this time, if you connect it to a voltmeter, this voltmeter will read a voltage. That voltage is big V. What is that? Terminal potential difference. Okay, so this will be like say 1.3 volt. So that is slightly lesser because it is not reading the EMF, it is reading the terminal potential difference. So that is what the first definition given in the textbook talks about. When no current is drawn from the cell, that is when the cell is in open circuit, the potential difference between the terminal of the cell is called as electromotive force. Okay, so this is terminal potential difference. This is EMF when there is no current drawn. Okay, but there's one more way this EMF and terminal potential difference can be same. This is one way because this is literally, it means terminal potential difference. That is in an open circuit. So in that case, EMF is equal to V. If R is zero, okay, that means the cell does not offer any internal resistance. So that time E is equal to IR, that is E is equal to V. Okay, so this answers the question, when will EMF be equal to terminal potential difference? So the first one, when the cell is in open circuit, when there is no current drawn, then if you measure the potential difference between the terminals of the cell, which is called as terminal potential difference, that will be equal to the EMF. And the second one is when there is no internal resistance offered by the cell. It depends on electrodes, material of the electrode, and the electrolyte that is used. And it does not depend on the shape of the electrode, the distance between the electrode, and the amount of electrolyte in the cell. So when you're talking about a cell has electrolyte and there are electrodes. So it depends on the material, okay, like whether they are zinc or copper or carbon electrodes. It depends upon the electrolyte, whether it is sulfuric acid or zinc sulfide. Okay, you have cells like lithium ion batteries and so on. What it does not depend on is the shape of these electrodes, okay, how they are. They are generally like rod or plates. What it does not depend is the distance between the electrode, okay, and we are talking about the EMF. And it also does not depend upon the amount of electrolyte. So the amount of electrolyte determines how long the cell will continue to give the potential difference. It does not determine the potential difference. Okay, and the other factors on which the internal resistance depends is the surface area of the electrode. Okay, so here it matters that if it is cylindrical or whether it is in a form of a plate. So larger surface area means less internal resistance. Okay, so the car batteries generally have electrodes which are like plates. They are like this. The electrodes are like this, plates. Okay, so larger surface area means less internal resistance. More the distance between the electrode, greater the internal resistance. So EMF does not depend upon the separation, but internal resistance depends. So more separation, more internal resistance. Nature and concentration of the electrolyte. So less ionic the electrolyte or higher the concentration, greater will be the internal resistance. So more concentration, more will be internal resistance, and more temperature, less internal resistance. So if the temperature is higher, the resistance offered will be less.